unique individual to the podium. Please join me.
Thank you. Thank you, Dharmendra. It's a pleasure to be here. The topic of this talk has to do with really conversational interaction. In particular, what we're focusing on is conversational customer service. This is a market that has zero automation today to speak of. I mean, there are a few very simple automated systems, but this is a multi-trillion-dollar market. This is probably where we're going to see the first $1 trillion a year sales company. And so what I'd like to do is just start off with the science underlying this. There is a theory called confabulation theory, and there is a new book that is coming out this summer from Springer Verlag called Confabulation Theory, and order forms are available here. You can also buy it on Amazon.com. It's a pre-order, of course. But so if you like what you hear or want to know more, there's a unified source of information that you can access. There's also, I'll give you a URL for an encyclopedia article that's online. You can go and get it while I'm speaking. This is a scientific theory that looks at cognition as a universal phenomenon. I don't think cognition is confined to any specific class of animals other than those with no brains. So if an animal has a brain, it pretty much is assured of being a cognitive animal. So cognition is universal. How did that come about? Well, in terms of confabulation theory, this is sort of the overview. The idea was, oh golly, that's a feature I don't like. The reality is that the Earth has been around for about 4.5 billion years. And at the beginning there doesn't seem to have been any life, and then life did emerge very rapidly. We don't know when. It's a question mark. But for a long, long time, for billions of years, life was in the form of microscopic life. Life that was, of course, building the base for today's life forms, but which of course are still dominantly microscopic. I mean, we can't lose sight of the fact that, you know, even though we think of ourselves as being supreme and so forth, numbers-wise we're a tiny minority. Those of us who are macroscopic animals, negligible minority on a numbers basis. What happened was about 1 billion years ago, the first animals came along that seemed to have nervous systems of significance. And those nervous systems basically served one role, and that was to increase the fitness of the animal by allowing sensors to be hooked up to effectors, namely muscles. And so you started getting articulated bodies with muscular components that could articulate them, and you started seeing behavior that was purposeful. However, that didn't go very far. If you look back 1 billion years ago, the animals were very crude. Along about 580 million years ago, an amazing thing happened. And this is one of the most fascinating parts of the story of Earth and its life forms. And that is that the atmospheric oxygen concentration suddenly zoomed upward to modern levels. Now, why this happened is not known yet, but it did happen. It's been basically documented by two different, totally separate lines of argument. The references are down here at the bottom. And this happened about 580 million years ago and led to what's known as the Cambrian explosion of species. It was at this point that a transition occurred from this basic kind of macroscopic motile animal to the early cognitive animal. Now, it seems likely that this invention occurred at that time. Of course, we don't know we don't know yet. But here's the idea. The idea was that you had developed nervous systems for the purpose of manipulating groups of muscles in coordinated, purposeful movements. And that mechanism was redeployed in a new way to move groups of discrete objects called modules, which now, however, reside in the brain. These are bits of discrete brain tissue, what we today call the cerebral cortex in humans, which are manipulated exactly like muscles because the same mechanism is used to manipulate them. So what is thinking? Thinking is movement. Thinking is nothing but a phylogenetic outgrowth of movement. It's a series of coordinated contractions of these muscles of thought, which in fact in our case make up our cerebral cortex. As this theme became so successful, because, and by the way, you might wonder, well, what is this called? What is the result of these operations called? It's called cognition or thinking. And all animals with brains do it. Now, this may be a bit shocking because you say, well, a bee has a brain. Is it cognitive? Yes. How about an octopus, an invertebrate? Yeah, very much so. And so are vertebrates and, and so forth. So, and ourselves. The bottom line is that this is a universal design that's been utterly conserved and added to. There's an enormous number of additional systems that grew out of this. Now, this talk will stick strictly to the cognitive mechanisms. We're not going to talk about, for example, the learning control mechanisms. We're not going to talk about the action evaluation mechanisms. There are many other subsystems of the human brain and many other animal brains that we're not going to even discuss. But the book does briefly, at least it lays out what those are and why they're there and what they do and so forth. So that's the essence of it. Now, if someone's going to claim that thinking is just exactly like movement, that seems extremely weird, and that's what it is. It's alien, in fact. Compared to all other approaches to information processing, this is utterly alien. This is totally unexpected and different from what people have been thinking. So let's do a very quick run-through, and I have to make it quick because all of these ideas, I want to emphasize, have consequences. If you really have a comprehensive, complete model of the essential mechanism of cognition, well, then you could apply that model to practical problems, and we have done so. And that's what I want to focus most of the time on, or at least a great deal of the time. But it's important that you understand at least the essence of the underlying scientific theory. Now, just as a prelude, it's important to understand that I don't think there is one neuroscientist on Earth who understands this theory or could possibly believe it. This is so counterculture, this is so weird and out of sequence from what people think in general, that this is not going to be digested easily or thankfully. And so, don't expect a huge uprising of neuroscientists embracing this. That's absolutely not going to happen. Neuroscientists are going to resoundingly ignore this for the most part. A few will begin entering that first phase of the grief resolution process, which is called denial. Denial is always a good sign in science. The essence of it is this. Cerebral cortex consists of a large collection, about 4,000 roughly. These numbers are very crude. I'm sure they're wrong, but I don't know by how much. But I'm just going to give you some numbers because it gives you a feel. These modules, as they're called, are the functional units. They actually include a bit of thalamus as well as this large patch of cortex. There are about 4,000 of them, and I'll describe what they do. That's very important to understand that there is a specific, explicit statement here of what they do. That's all they do. There's nothing more. And by the way, it's important to realize cortex does other functions. I'll even allude to one of them, or a couple of them. And so this isn't the only function of cortex, but it's the main function. It's the reason why cortex exists, to carry out cognition. Within each module, you have about 4 million neurons. So these are huge modules. These aren't the columns of Mount Castle or the hypercolumns that he later discussed, or these other kinds of modular elements. They're much, much larger. However, yesterday you heard Professor James Anderson speak, and he talked about networks of networks. And that probably is in the same basic realm of thought. So you'll see as you go forward here a number of parallels with Professor Anderson's talk. That's not accidental. Professor Anderson is, in fact, my #1 main intellectual source of inspiration. And so I have very heavily been influenced by his work, and you'll see that very clearly. And in fact, as I say, I don't think that our thought processes are very far apart. But that's for him or others to analyze. Now, what is the purpose of a module? The primary purpose of a module, the only purpose in cognition, is to represent one attribute, a single attribute, that an object of the mental world might possess. Now, this object may actually exist in the external world, or it may be like Alfred E. Neumann that exists only in a mental world. It's a fictional thing. It doesn't matter. This module describes that one attribute. And how does it describe that attribute? It describes it by assigning one of a large number of symbols. Now, human cognition is superior to animal cognition in general, for other animals, in the sense that, oh golly, that we have maybe more symbols. And it turns out that Soren Solari, who's in my lab, has hypothesized that this is because our modules are just a tiny bit larger. And as his work proceeds, we'll maybe have a demonstration of that in terms of having a cognitive power grow much greater than linearly with the amount of brain tissue, which could help account for why humans are so intellectually gifted. Now, each symbol is a small collection of neurons, maybe 60 neurons, out of a total of about 450,000 neurons that are part of cortex, part of the little cortical patch, the module, that are devoted to this function. There are many other groups of neurons that do other things, but this roughly 400,000, 60 of them at a time. So this symbol 1, if this little patch is used to represent names of things in your brain, one of those little collections of neurons would be assigned to the word mother. Another one would be father. Another one would be JFK. Another one. There'd be thousands. And in fact, I would contend that the most brilliant people probably have 1 million symbols in some of their modules. Now, what is knowledge? Whoa, what do you mean, what is knowledge? I mean, you're going to define cognitive knowledge once and for all? Yes. What it is essentially, and by the way, if this looks Hebbian, if this looks a lot like what Professor Anderson was saying, that's exactly what it is. What Hebb believed was that you had these groups of neurons and that links would form between groups, that the meaningful linkages of learning were links between groups that happen to co-occur in their activity. That's precisely what this theory suggests. So what you have here are 2 different modules, one of them representing names of objects. That's this one right here. And then another one over here representing the colors of an object. And what I'm doing is looking at a red apple. And so over here what we have is a collection of 60 neurons that happen to represent the English word apple. And over here we have a collection of 60 neurons that represent the particular red color of that apple. And there are many others, as you'll see in a minute. There's thousands of these modules, many of which could bear upon the mental object apple. Now, if these keep co-occurring, which they do because I keep looking at these red apples, what will happen then is the connections between these neurons here and these neurons here will be strengthened. Now, anyone who understands even the most elementary facts of neuroscience knows that this couldn't possibly work. This is absolutely not possible because these connections don't exist. There's no way that 60 neurons over here in this part of cortex could ever actually directly connect up with 60 neurons over here. The probability of that being possible is 0. But we'll get to that in a moment. Here's another example where now more attributes of that apple that I'm looking at are being represented. So, for example, down here we have a symbol that is representing the odor and taste of the apple. Up here we have one, this is sort of a somatosensory area that's representing the skin texture of that apple. Over here is a motor representation of the chewing that I might go ahead and carry out with respect to the apple, and so forth. And of course, these co-occur with each other all the time, and so each set of neurons, each symbol has, and they're of course not all shown here, are pairwise linked. That's most important. The linkages are pairwise only, and you'll see why in a moment. This is the basic way that a knowledge link gets implemented. These are the neurons here in lower layer 3, perhaps. This is still being looked at and investigated. In fact, Soren Solari is very involved in that. But essentially what we know is that those neurons do send connections to other neurons here in layer 2, which then become an intermediate representation for this symbol. And then those actually go ahead and finish the linkage to the target symbol. So here you have the 60 neurons that represent the word apple. Here you have the 60 that represent the color of that apple. And by this two-stage process, you are able to make enough of these linkages that forms the knowledge link. These synapses over here are the ones that are strengthened. Now, this is precisely what Moshe Abeles has always been talking about, but instead of being just a vague concept that might be used in 49 different ways, this is explicitly saying that it's used for one and only one purpose, and that is to form these knowledge links. Now, how many of these knowledge links are there? Well, you probably possess billions of them. That's not a misprint. What does that mean? It means that philosophers and psychologists and cognitive scientists have vastly underestimated your intelligence. Humans are much more intelligent than anyone imagined. To achieve this kind of knowledge possession, you have to actually accumulate knowledge at a far greater rate than one knowledge link per second. So if your child ever comes home from school and says, well, I didn't learn anything today, it's not true. They probably learned 100,000 things that day. And that was a slow day. Now, by the way, there are only 4 parts to confabulation theory. The first one I've already been through, the idea that each module represents a single attribute of a mental world object, and that it describes that attribute by selecting from a list of discrete symbols. Now, of course, I'm not talking at all about how this all develops. That's a story we couldn't possibly touch. The second component of the theory, element number 2, has to do with knowledge links and their properties. Now, the third, there's only 4. There's only 4 components to this theory. The third one is, what's information processing? What is thinking? How do we think? Well, I'm going to actually tell you. And this is it. There's nothing else. It doesn't matter if you're talking about moving or playing chess or speaking or trying to work out tensor analysis problems. This is how it's done. Every single aspect of cognition is carried out using a single information processing operation. And it's really weird. Here it is. Let's imagine that these are modules over here to the left, 4 of them, that have each carried out this operation a short while ago, a few, maybe 100 milliseconds ago or a few hundred milliseconds ago. And I'll just say that what ends up being the outcome is a single conclusion symbol. So one symbol is selected as the conclusion. Now let's look at a 5th module as it goes through the thinking process. What happens is that you have knowledge links from this symbol to thousands of symbols in this module. And those knowledge links are being fed by the excited neurons, the 60 neurons that represent symbol alpha. And so you have all of this excitation being delivered to groups of neurons over here. Similarly from beta, gamma, and delta. The net result is that, sorry, my finger wanders over into the wrong territory and things change. The net result is that you have different levels of excitation of these different symbols. And that's shown here, where some symbols are only receiving knowledge links from 2 of these assumed facts, as we call them. Others are receiving inputs from all, and they are having much higher levels of excitation. One of these has a highest level of excitation. Now, some of you are saying, oh, no, I know more about neurons than you do, because neurons are so inaccurate as mathematical functions, they couldn't possibly accurately accumulate this excitation. Oh, you're exactly right. That's not how it works. This is done in the most clever design that in fact uses the fact that a symbol is an ensemble of neurons. And it's only the statistical ensemble excitation that matters. And that, by the central limit theorem, that actually cures all the numerical inaccuracy problems that you would suffer with just using one neuron. Anyway, the net result is that this module is then commanded. Now, I have to emphasize this. Is commanded deliberately, just like in the movement of a muscle, the contraction of a muscle. It's given a command, and when that command arrives, it thinks. What's that process? It takes these thousands of excited symbols and ends up having them interact with each other on a very, very fast parallel basis, which we don't understand the details of yet. We have some understanding. I'll show you some hypotheses in a moment. And the net result is that a very short time later, probably 100 milliseconds or less, one of these collections is now blasting out its information on a synchronous basis. Are the others shut off? No. But they are, in fact, not, their capability to signal is shut off, is diminished. So the net result is that you end up with one symbol, the most excited symbol being the conclusion. And that's how thinking works. Now, how could that possibly be a universal information processing operation? Isn't there some kind of mathematics under this? Well, we'll get to that in a moment. The bottom line is that the number 4 and last part of this theory is that every time one of these operations occurs, you're probably saying, well, what is that called? What is this operation of information processing called? It's called confabulation. It's a winner-take-all style thing, but as you'll see, there's a bit more to it. And you'll see why it's called confabulation here in a moment. Anyway, the net result is that once the confabulation is completed, you now have a new process, which is this highly excited winning symbol, the conclusion, through a set of axonal links going within cortex to another set of neurons, causes those neurons to issue what's called an action command. And this is ultimately what causes new behaviors, new movements, and new thoughts. So the net result is that the end of every thought process is the launch of a new set of behaviors. Isn't it odd? I mean, neuroscientists never talk about where behavior comes from unless you're talking about, like reflexive behavior or some sort of gastronomic behavior, because we have good ideas about that. But this problem of where is it that my movement of tapping my watch comes from? What caused that? What specific event in my brain caused this thing to happen? Now I'm waving my arms. Why did that happen? This is why. That's it. There's a lot more to say. No time to say it. There is a mathematics underlying this, and it's totally unexpected. As you know, there's been this huge rave of activity with regard to Bayesianism. It was almost a religious fervor that swept through mathematics and engineering and so forth. And in fact, the brain isn't Bayesian. Bayesian analysis is quite different than what cognition does. And so this theory explains precisely what it is. Namely, you choose that conclusion, epsilon, based upon these assumed fact inputs that you use during the confabulation to choose epsilon. You choose the conclusion that's most supportive of those facts. And that's the way cognition works. This probabilistic quantity, which of course is a formal quantity, it's not computable really, but it's called cogency. And that's the underlying mathematics. And yes, you can show that this has universal potency. Now, let's apply this to a very simple example. Same architecture. Now I'm going to show you more details. What we're going to use is thousands of symbols in each module, each one representing a word of English, uncapitalized. And then what we do is we expose this system to strings of English words selected out of newspapers. So this is, we put the first word in the string here and light up the symbol that represents that word. That's an assumed fact. Then we put in the second word, the next word in the string, light up its symbol, and so forth. And then we put in the fifth word, and then we actually create knowledge links on the basis that a symbol here has co-occurred with a symbol over here frequently during the parade as you march down this huge string of examples. Now you might wonder, well, what happens if you put in Chinese text? It works just fine too. It doesn't matter what language you're talking about. In any event, once you have done that for a while, in this case, we accumulated a set of 5,251,335 of these knowledge links by just exposing it to examples of well-written English strings of 5 words. By the way, the person who did this is here, Dr. Robert Means. If he would stand up for just a moment, I'd like to acknowledge him. He'll be mentioned again. The fact is that this works. You can now go ahead and put in a totally fresh string that it's never seen before, for lack of a, and then confabulate over here in this fifth module, and the word you get back is unified. Well, that makes sense. One of the questions is, what if the neurons are still not really perfectly accurate? Because you don't have much numerical accuracy in a statistical ensemble of neurons. What if the second most excited symbol became activated by accident? Well, it's blockbuster. For lack of a blockbuster. What about the third? Comprehensive. Why, these are all good. So the point is that one of the realities is these computations do not have to be high precision, and if you make a mistake, usually it doesn't matter. Now, let's just, again, I wanted to highlight the fact that there is a rational scientific underpinning to this. This isn't just some wild and crazy engineering theory. This is actually completely consistent, as far as we know, with the facts of neuroscience. And in fact, it ties together many of those facts in what I see as a very pleasing way. Again, that's for others to judge. This is a cross-section. You can just see where it's at. And this is thalamus here in the center. These represent thalamus. And then, of course, you have the cerebral cortex here. And so what would a module, this is the 6-layer structure of cortex. This is kind of what a module would look like. It's a patch of cortex paired with a little bit of a particular part of thalamus. And to look at the neuroscience basis for this theory, Soren Solari has produced this called the Human Confabulation Neuroscience Knowledge Environment. This is a compilation of hundreds of the very best neuroscience reviews of this neuroanatomy. You can see here most of the subcortical structures of the human brain down here below, and their connectivity with cortex. It also illustrates the connectivity of cortex with itself. There's an enormous amount to say here. Our hope is that we will actually be publishing this in the next couple of years to provide the community with this kind of panoramic introduction. Our belief is that many people who currently know little about neuroscience are going to want to know a lot more. And so the purpose of this publication will be to bring to you this integrative chart as well as reprints of all of these key references that review the best knowledge that has been accumulated by neuroscience about the details. Now, we could go on and talk about how confabulation might actually occur in the brain. Where does that thought command signal, those blue lines, come from? And then how does thinking actually work with the cells? But we're not going to do that. What we're going to do now is move on to the practical world. Again, this is a complete and exact theory of cognition, which means that you should be able to apply it by building little simulations of these bits of brain tissue and then having them interact and see what happens. Well, here is a specific example of what we're doing. We're not done with this, but I'm going to review some progress that we've made. Down here at the bottom, now again, where are we going? Conversational customer service automation. So in other words, you would be able to call your bank, you would be able to call a retailer, you'd be able to call a home improvement company, you'd be able to call an automobile dealership, and just chat naturally back and forth. The machine would understand what you said. For example, if you were to go to an automobile dealer on the phone and say, someone just hit me in the rear and I need a new taillight lens. And then it'll say, well, what year, what model and year of car do you have? And then you'd go and talk about it, and they'd say, yep, we have the part, it's $49.95. Come on down, we'll give it to you immediately. And we'd be delighted to put it in for you. So that's the kind of thing, that's so far beyond any capability that exists. It's just pure science fiction. So I ask you, as you look at this, to remind yourself repeatedly, over and over again, that the specific demos that I'm going to show you here, the actual experiments, are real. This is not some kind of hope. This is not a dream. This is accomplished work. And I think you'll gain an appreciation for how potent this line of investigation is. And of course, our dream is that this will be taken up by thousands, if not millions, of people in the very near future. At the bottom here, what you see is the sound coming in from a microphone. Wearing little headsets is fashionable today, but most people hate that, and there's no need for it. You can have a room where sounds can come in from many sources, including the speaker you wish to attend to. You put it through some pre-processing, which I'll just give you a brief input, I'll show you a little bit about. You represent it here. Then you apply a cocktail party processor, which separates out the sounds coming from the attended speaker. And then the next thing is you do some word matching so that you can come up with candidate words. You may not know, but speech is inherently ambiguous. If I were to have a conversation with you and clip out words, individual words that you spoke, and then play them back for you a year later, you couldn't recognize many of them. You'd be amazed at how few you could recognize by themselves, without context. And that's the way it is for a machine trying to understand what you're saying. The words you speak are, in many cases, highly ambiguous. What this system does is it doesn't try to figure out what word you said. It doesn't even attempt that. It's a much simpler thing than the systems that have been built commercially. What it does is it attempts to list all the words that could have been the word you spoke. With high probability, the word you spoke is on that list. Okay, actually, you get several strings of those words that are different candidates, but I'm just going to look at one. Then you have to do some post-processing to figure out which words were spoken because they hang together in terms of their coherent meaning. And that's what we've now done, and I'll show you that system. That's a new result. And then we're going to have to take the input, which is colloquial language, and reformat it, because internal to our system we use proper language. That's something that we'll get to in a minute. How do we do this cocktail party thing? That seems impossible. What happens is that the system uses the last couple of seconds of speech, and it learns, in a 20-minute session, let's say, it learns the speech patterns of a particular speaker. Let's say some member of the household, because this is a little box sitting at home. And during that time, it basically forms a predictive model based upon confabulation architecture. And that's over here. So every 30 milliseconds, it makes a prediction of what sounds you might speak 30 milliseconds later. And that becomes a list of specific sound symbols that might be activated by your speech. Now, only a small number of those are actually going to be activated. That's illustrated down here. Now, in our case, we use about 11,000 sound symbols to represent the currently incoming sounds. And you can see here that they're coming from multiple sources. Source one is the attended speaker. The cocktail party processor makes a prediction of which symbols might actually have the sound from the attended speaker. And then, in fact, these three came in. It's usually about 10 in the case of our system. And you're saying, well, how do you know that works? Well, not only does it work, but it'll work where you have 5 speakers total, and they're all the same volume, and they're all speaking different material. One of them starts a couple seconds early, so you can actually start tracking that one. And then you're able to actually keep tracking it in the presence of this background sound. A mixture of 5 speakers into one microphone, nobody on earth can do that effectively in this kind of very short time period. Some of the methods that have been developed, such as independent component analysis, just simply won't work in 30 milliseconds. Now, what about this sound input stuff? How far are we along in that? Well, this is an example. Up here at the top, you can see the raw speech waveform. What we have are some, we have sort of crude models of the cochlea and the brainstem auditory nuclei. The outputs of those are shown here. And then down here, there are the 11,000 symbols that we have in this sort of cortical level representation. And time goes on to the right. Let me actually show you one of these in operation, just so you can see that it exists and it works. So what I'm going to do now is just keep talking, and I'll describe this a little bit. As you can see, my sound waveform is up at the top of the screen. And as I stop talking, it stops bringing in data. This is the output of this brainstem, or well, the cochlea / brainstem auditory nuclei. Don't get excited. I mean, this is not a very realistic thing, but it does follow the principles of the actual biological system. And then down below, you see the responses. Roughly about 10 symbols are activated by the sound at each moment of time. And you can see there are breaks between my words. However, it's quite possible to do co-articulation where there are no breaks or very few breaks between words. The vertical lines up here have to do with the segmentation of the sound stream into words, and it's too much to talk about. But anyway, you get the idea that this is not some dream. This is actually stuff that works and that represents a research process in its... yeah, so let me go on here. Now, So the big thing is that the output of the acoustic processing is a string of lists of words. Here's an example. So the first word, Japan, was unequivocal. It got that word, and that's the only word that it feels you could have spoken. Then here are a set of words that might have been the second, the third, the fourth, and so forth. The fact is that this is highly ambiguous. What you need to do to disambiguate this is choose one word from each list. It's like a Chinese menu. And this is the architecture that does it. In this particular case, we're dealing with whole English sentences. And this thing has actually been exposed to millions of sentences from news stories. So it's proper English. There's a lot of restrictions and limitations on this. But it's obvious how you would expand this to arbitrary language and colloquial language. So what you do is you put your lists. Here's another example of some ambiguous lists. And these are not actually from an acoustic analyzer. These are just examples to give you an idea of how it works. And so what you want to do now is you want to use all of the accumulated knowledge links, of which there are hundreds of millions, to decide which words hang together properly and make sense. Now, nobody has done anything like this. This is really novel, and in fact, it's something that doesn't represent a standard research problem because nobody could possibly solve it. The fact is that what you do is you do a movement process where each of these little tiny muscles of thought, remember each square here represents one of these thalamocortical modules, is given a signal, a thought command signal, that slightly tightens it up. Now, what does that tightening of the little muscle of thought do? It simply further contracts the list of possible conclusions. So you're slowly contracting these lists, converging to an answer, but at the same time allowing those symbols that are left to communicate with each other via these knowledge links. Again, is this weird or what? How in the world can we do information processing with an analog control signal? All of you are familiar with the idea of an instruction set for a computer and a computer program, which is a series of discrete instructions. Okay, now take register A and add it to register B and put the result in register C. This isn't like that. The brain does not work that way. The brain works on the basis of analog control of a gradual convergence process in many separate and discrete pieces of hardware together, precisely as we end up executing movements, using the same neurological control mechanisms that were originally built for movement. What's the result? Well, let's look at it. Here we have the ambiguous word lists in this string. We go ahead and we allow one round. We go around and let all of the lists communicate with each other. We call that a swirl. That's this red arrow going around. And the net result is that the set of possible conclusions is narrowed. So we've tightened up these little muscles of thought. Then we do swirl 2, and then we finally end up with our conclusion on swirl 3. In a real system, like on a conversational server, this would take just a few milliseconds. The net result is we end up with a sensible string of words. Okay? We can do this all day. The knowledge, we're applying literally hundreds of millions of items of knowledge in parallel. Nothing like this has ever been seen before in information processing. Now, this, of course, that's the dream, right? The dream has always been, how can I apply vast amounts of pre-developed knowledge to a specific problem in real time? Well, here's another one. So again, we're doing 3 swirls. Swirl 1, swirl 2, and then swirl 3. Final answer. You get the idea. Here's another one. Just read the lists here. It's not easy to pick out. I mean, you as humans can do it, but it's not easy. It would take you quite a while unless you were actually listening, and then you can do it instantly. If there were an environment where you were really having trouble identifying the words, it would be very easy for you to cook this answer up. And by the way, there could be more than one sensible string. We get them all by doing, we can do this again. We just blank out these words. And anyway, it's enough. And here's one I chose that I thought was really cool. Anyway, total accident. I don't think there's time, but I have this system. Well, I'll just take a moment and just show it to you. This system actually exists, and it too will run. So this is essentially the demo of that system, and you can sit there. Now this is slowed down so you can read the examples, but it actually does this in real time. This is a real system that actually you can put in by the way, these are just randomly chosen newspaper stories. These are not like contrived examples. And it works almost all the time. It's very reliable. So anyway, enough of that. The fact is that this moves us in the direction of being able to do conversational customer service. And so let's just talk about that. What would it be like to have a conversational system? This is a system we envision. It's hypothetical. It's not real. It's called Chancellor. And look at how it would work.
Chancellor, it looks like we're...
Uh-oh, sorry. I think that cut it off.
Chancellor, it looks like we're down to the last few days of cat food. Please order some more.
Shall I order 2 bags as usual?
That would be fine, thanks.
2 bags of cat food have been ordered. They will arrive on Friday. We don't want Zeus to go hungry.
So the concept here is very simple, and that is that it knows all the family members because it's served this family for years. It knows all about how they go about their business. She says, we're down to the last few days of cat food. It's never heard that phrasing before. It doesn't matter. It instantly understands it's time to order cat food. It then proposes that 2 bags be ordered because that's the usual pattern in the family. You see the idea of effortless conversation. Notice there's clanking of dishes in the background because there are other family members eating dinner. The fact is we don't need to have, you don't have to wear a noise-canceling microphone. It works fine. The cocktail party processor takes care of it. You're probably wondering, well, how does it key up on the speaker? It actually uses the word Chancellor. It has a matched filter, a bunch of matched filters for each family member and their way of saying Chancellor. And then that's how it syncs up and segments them. Anyway, the bottom line is it then goes out, she authorizes the transaction. It goes out on the internet, it goes to the grocery supplier for the family, orders the bags, gets a delivery estimate, and then says the 2 bags of cat food will arrive on Friday. Then it goes into a conversational banter mode. And, well, let's play it one more time.
Chancellor, it looks like we're down to the last few days of cat food. Please order some more.
Shall I order 2 bags as usual?
That would be fine, thanks.
2 bags of cat food have been ordered. They will arrive on Friday. We don't want Zeus to go hungry.
Chancellor.
Now, you know as well as I do that that's impossible. That's pure science fiction. Many people would say that's 20 years, 30 years away. That's, even the most optimistic people can't imagine if they were given a huge bolus of cash, how they would build such a system. Well, I'm going to show you how. These are all the things, again, there's no time to go through this, but in effect, there's a whole bunch of different things that have to go on, such as keeping track of everything that's ever been said with family members, and then applying that context to future conversations. But in the end, the part of this that's the most difficult is how do you actually generate a cogent conversational response? That's this box up here, conversational response generation. Let me just give you a glimmer of how we might be able to do that. Now, this is, again, a real system. This system, by the way, before we go any further, The speech processing system that you saw a minute ago was built by a real human being who's not me. And that's Dr. Ciris Nemet Nasser. Would you stand, please, Ciris? And so, you know, Ciris has built the speech processing part of this. And now we're going to see another system that Bob Means has built. Bob, of course, built the system that disambiguates the lists as well. This is, you know, every time I say this, you're starting to appreciate that all I do is stand up here and talk about this stuff, that all the work is actually done by others. That's precisely correct. Here we've taken triples of sentences from news stories. So we take the first sentence, the next sentence in the story, and then a third sentence. It doesn't matter where they exist in the story, as long as they're within one paragraph. We put in literally tens of millions of these. And over that time, these co-occurrences are noted and knowledge links are formed. That's all it is just Hebbian symbol co-occurrence. Now, I want to emphasize again, these architectures have no algorithms. There's no rules. There's no ontologies. In this case, effectively, all we do is put in lists of words down here. So this module right here has a list of 63,000 English words and 8 punctuation marks. So does that one. So does that one. So do all these others, ... and so do these. The first sentence is put in here. Like, let's say the words were, the truck went. We put the word the in here by lighting up the symbol for the word the with a capital T, because it's at the beginning of the sentence. Truck, its symbol gets lit up. Went gets lit up, and so forth. Then we put the second sentence in here, the third sentence in here. For a long time, all it's doing is noting co-occurrences and creating knowledge links. Okay? Now, let me just say it because it's very important you understand. If there's ever anything in your life you've ever paid attention to, you need to go to that level of attention right this minute. This is the most important thing you've ever seen in terms of your career, in terms of the interests that you have in the area of information processing, both biological and technological. Now, once you have put in all of these millions and millions of things, the production of new knowledge links begins to slow down. Well, okay, then let's say that's enough. Now what we can do is we can take an entirely fresh news story that it's never seen before from a later period of time from a different newspaper. And in fact, we're going to use the Detroit Free Press. This was trained on a whole melange of different stories, probably mostly from the 90s and early 2000s. And then we took stories from a more current era. We put in the first two sentences from, we put in two consecutive sentences from somewhere within a paragraph of that news story. And then we allowed this progressive contraction swirling to occur over here, finally resulting in one symbol on this module, one symbol on this module, and so forth, the final symbol being a period. And so this thing creates output. Let me show you some examples that this system actually created by itself. Here is the first sentence we inserted. Again, these are from the Detroit Free Press. Several other centenarians at Maria Manor had talked about trying to live until 2000, but only Wegner made it. The second sentence we put in, her niece said that Wegner had always been a character, former glove model, buyer for Macy's, owner of Lydia's Smart Gifts downtown during the 1950s and 60s, and that she was determined to see 2000. Now you're going to notice something. This is full-strength English. This is not some attenuated baby book type English. This is the real deal in its most elegant newspaper form. Now, given those two sentences, you now go through this swirling process, and the system now converges to a string of words. Here they are. She was born in the Bronx borough of New York City. Now, is that a fact? No. It's a plausible next sentence, because that's all the system has seen. It's seen 3 sentences in a row, and now, based upon all of that experience, it's generating a third sentence. It is confabulating a third sentence. What does that word confabulation mean? Well, that's a psychiatric syndrome that is noticeable in people who have a lack of context information. So they come up with statements that are not factual, that are just made up from incomplete sets of assumed facts. And that's how all cognition works. And so that's why it's called confabulation theory. Anyway, the bottom line is that this is actually a grammatically correct English sentence, and it's extremely plausible as a next sentence. How in the world did it get that it's a she? Well, it says up here, her niece. That's the only real indicator. Of course, glove model would help you. What's this Bronx borough stuff? Well, it's just showing off. It's showing off that it knows a lot about New York City. Now, we could go on and on. Let's look at this second example here. This is just another example. First sentence, Michelle strengthened from a Category 2 to a Category 4 storm Saturday, with winds reaching 140 miles per hour, but it was expected to weaken before it reached Florida. First sentence. Second sentence, it acknowledges that... Oh, phooey. Thank you. The storm or its effects could strike... You're paying attention. Thank you. Could strike the Keys and South Florida tonight or early Monday, said Chrissy Williams, a meteorologist at the National Hurricane Center in Miami. And now what does the little architecture produce? Forecasters warned residents to evacuate their homes as a precaution. Now, I've got page after page of this. Well, in fact, let me go through these so that they can be captured on video. We got that one. Here's the second one. I'm not going to go slow enough for you to read these, but I will stop on number 5. Our videographers are capturing these. Let's look at this one. Last summer, when we released these results, a person who's literally the world's premier chronicler of the world of AI, Mr. John Markov of the New York Times, did a story on this. And you can see here, this is the example he chose down here at the bottom. He started his goodbyes with a morning audience with Queen Elizabeth II at Buckingham Palace, sharing coffee, tea, cookies, and his desire for a golf rematch with her son, Prince Andrew. Second sentence that we put in. The visit came after Clinton made the rounds through Ireland and Northern Ireland to offer support for the flagging peace process there. The sentence produced, the two leaders also discussed bilateral cooperation in various fields. Now, let's just look. What if we were to take this system now and expose it to much greater amounts of context and actually use new material that was created by a superb customer service representative, or actually a whole army of them, working for a particular company? We could extend its capabilities now to generate cogent responses to this particular kind of practical application. Now, some are going to be skeptical, and you should be. Skepticism is very much called for. But these results have to be looked at and considered in your skepticism. The fact is that this is intelligence. This is actual intelligence in a machine. Now, you can argue, oh, it's not the kind of intelligence I need to see to call it artificially intelligent. But in fact, regardless of what you believe, if you're honest with yourself, you will in fact agree that this is real artificial intelligence of a kind. Can we go further? Of course we can, because we know what to do now. In closing, again, I would like to offer this as a reference if you would like more information. This is what the cover looks like. This is not the book. The book, of course, is a normally bound book. There are forms down here on the table in case you'd like to order it or get more information. I want to also emphasize this reference. This is actually an online encyclopedia article in a computational neuroscience encyclopedia. Really great resource that you can go to immediately. Research sponsors, thank you. And again, my colleagues who have actually done all the work. And of course, my cat. The cat was already featured in the Chancellor vignette. The essence of this is that this discovery would not be possible if it weren't for this cat. He's 17 years old this month, and he and I have walked together in the morning before breakfast for almost every day, the majority of days certainly since 1990 when he was born. And it was through observing him that these principles, these 4 basic principles of how cognition works, were discovered. The process is very, intimate and strange, and it involved years and years of interaction. But nonetheless, without him, this wouldn't exist. And so, thank you, Zeus. Thank all of you for your attention.
I'm Paul Alapena from Aptima and Brown. I'm just wondering, with the demo that you gave, you've shown plausible generative sentences. Are the contexts deterministic? If you fed the same 2 sentences in again, would you arrive with the same plausible sentence?
Excellent question. The answer is that this particular system is, the simulations of the brain tissue are basically deterministic. And so yes, this will give you the same answer. If we were to go in and introduce just a bit of noise, like you're undoubtedly going to find in a real nervous system, if we were to introduce fatigue, for example, where the answers that won one time are now tired, and so you get a different answer the second time, but not a bad answer, I think we would see that. And so that brings up, I think, frankly, the theorists who deal with fundamental issues of information processing, they're going to have so many happy decades now. Because this is going to be so interesting from that fundamental mathematical standpoint. And you're raising one of the key elements here, that this is really not, in any kind of realistic biological system, deterministic. And yet, it's highly robust.
Hi, I'm Martin Wren. So, observing one of the modules in your network, you describe how you collapse the evidence or the input into that module into one active unit. And in another of your examples, you have...
Look slowly.
In another of your examples, you have at one point a number of active units, and then it's progressively collapsed, and eventually end up with one. And a third way would be to keep sort of like the whole probability distribution and operate on that. So in general, as cognition goes on in the cortex, do you believe that that the process goes on like you collapse all the evidence into one active thing, or do you more like keep the whole probability distribution or a longer list of alternatives if you do consecutive steps of cognition?
That's a very good question. The answer is that they both occur every time. Because while you're still going through the thought process, you are keeping open a combinatorial explosion of possible final answers. But in the end, it's essential that you converge to an answer. And so in other words, if some sort of a crisis erupts, like a sudden earthquake or something, and there's no earthquake, oh, never mind. The fact is that I would have a decision to make as to what kind of behavior to launch. What's known from endless amounts of psychophysical data is that those decisions are decisive. Now, you can dither. You can end up with one decisive decision, which is then changed to a different decisive decision. That's a different thing. But the behavior of cortical processing is decisive. You end up with one answer in each area. Now, in the case of sound processing, it could be that you'll end up with 2 or 3 possible strings that are viable. And then you have to wait a moment while more sound comes in, and then it disambiguates. So you can do that. You can keep the computation from ending for a moment and then end it. But yes, you're exactly right. Both of those are essential in almost every computation. Maybe one more, if there are any.
One at the back.
I'm Dave Nola from UC Merced. I want to push on this decisiveness point a little bit more. When you do something like tap on your watch, when you use this kind of motor analogy, it seems like there's some continuous amount of opponent process, muscle tension that's applied, and there's also refinements in timing and the like.
Right.
So I'm curious how you imagine this architecture would fare, where the outputs really aren't symbolic, where there needs to be a graded response of some kind.
You know, colleagues and I, many colleagues and I have had this discussion, and that's a wonderful point. That's the part of this theory that's the hardest for people to swallow. The idea that these outputs are hard things. These inputs are hard things. But the inputs really aren't hard things, and that's essential. If you look here, at every moment in time, there's actually a whole multitude of symbols. In this case, about 10 symbols that are responding to the sound. And so it turns out that all of the primary cortical sensory regions are almost certainly operating in a multi-symbol mode all the time. In the case of motor output is extremely paradoxical. And in fact, people have spent a great deal of time in the last few years, last 10 years, really trying to understand the codes. And the codes do not appear to be pure symbols. They appear to be what amount to mixtures of symbols. In fact, just last week I was at a neuroscience review where people actually showed that the outputs were blends of what appeared to be fixed ensembles of neurons. The fact is that that's exactly right, and the outputs within, say, a motor area or in an area that's actually controlling these thought processes are blends of symbols, never one symbol. And in fact, that's reflected in the anatomy. So that's perfect. All right. Thank you.
Once again.